Good morning, and thank you so much for inviting me as an academic to this fascinating event here. And also, thank you for not also inviting me as an academic, but also inviting me as a database person. So we are actually dealing with data management, and we are working hardware, software co-design. So how can we make data management more efficient in the light of modern hardware? So we just heard about the move of traditional row-based, tabular, structured data, and we know all about this unstructured data. We heard about the yottabyte scale, and we also see a significant move from the traditional database mentality down to open table formats, to modern systems like Apache Hudi, Iceberg, data lakes, etc., etc. So what actually is interesting, variety is king on the data side. So if we look on the hardware side, what we also see is plenty of new stuff is coming up. We have GPUs, we have TPUs, we have a huge plethora of different CPUs, we have different memories and storage, the boundaries are kind of merging. So again, variety is king. So where does that actually lead for the data management community? The data management community is kind of somehow squeezed in. On the one side, we have these evolving data-intensive applications. We are kind of the foundations. We are driving ML and AI applications. We have to provide a consistent perspective on the structured and unstructured data. But on the other hand, we actually have to face the challenges coming along with this new plethora of modern hardware devices. So, and what kind of basic architectural principles do we have? Well, there's on the one hand the traditional make systems bigger and bigger. And so this is kind of the traditional way of doing it. This is run your database system, install your database system, and whenever there is more demand, just move it to a bigger machine. On the other hand, more or less the modern style of data management is, of course, scale out. Many, many machines, hundreds, thousands of machines running data analytics jobs, somehow having and representing this kind of new world of data management. So what does it actually mean, and are those kind of principles, a scale up, a scale out, is this really enough for coping with the challenges to come from a technical perspective? I mean, we can actually, when we actually look at the design space where data management systems in the wider sense are positioned, we can actually have multiple dimensions. And one dimension is more or less scalability. Of course, a machine with 1,000 cores, this is kind of common, this is commodity, but we have to go well beyond a 1,000-core machine, etc. So moving data is evil. We don't want to somehow move petabytes around just to filter them out and throwing them away. So on the other hand, are we able to perform elasticity? So when workload changes, react to sudden workload drifts, changes to spikes, etc., is this the right way to go? How do we actually deal with this plethora of different computing devices, different memories, different storage systems? So I think there is kind of a need of a second dimension for a design space, but this dimension comes for a price. I mean, if you look just as a nice example, if you look at a very simple data management operator, the same operator, same data set on different devices, you have completely different performance characteristics. So you have to deal with this. If you look at the memory, energy consumption, how are we able to tackle energy awareness? This is dark silicon is hitting us, so we have to somehow figure in and factor in these characteristics. Looking even further, and as an academic, this is our job to do, looking further, we have to deal with other non-functional characteristics like taking resilience. So how do we actually handle defects, defective components, etc., etc. The question is, for this design space, is scale out or scale up, is this really the right way to go? And to achieve this elasticity and to achieve and cope with the variety of different computing devices. So luckily, we have third dimensions. So database people or big data people love these 3 Vs. We have a third dimension, and this is somehow leading us to variability dimension. So a couple of years back, the notion of composable systems came up. And the idea is that we are now able to reconfigure our computing device. And this is what I actually call scale flex. So what is the promise with this scale flex? Well, the traditional computer as we know it is just gone. That's the idea, to some extent, in the extreme. And the promise is that it's a fully disaggregated environment where we have the compute store, where we have the compute, we have the memory, we have the storage, we have the communication part. And there is some kind of magic fabric in the middle, and this magic is kind of connecting all the different components, forming by software what we now call a computer. And even going forward, the promise is that we have a common memory space that kind of achieving a scale-up characteristic by scaling out different devices on different levels. And when I first saw this, I was totally fascinated. I said, I really have to have this. So I took my machine, I ripped it apart, went to the basement, into my workshop, and just cut it and tried to disaggregate memory and compute. Obviously, that was not so successful. So luckily, we have standardization going on in one extremely promising way is CXL. So CXL is a set of protocols, and it's covering a huge consortia, defining all these virtual fabric, how the different components, how the different devices are communicating and working together. So for the techies among us, CXL defines 3 sets of protocols, one for handling the I/O, so that there is kind of a cache-coherent direct storage access, a direct memory access. There is CXL cache for implementing the cache coherency, and there is CXL memory allowing remote memory, highly disaggregated memory, and mount it into my local compute unit. So, of course, at the university, it's our job to take whatever we get in modern hardware and do kind of pathfinding. So how far do we get? Is this kind of a viable solution? Can we somehow build on top of this? And what are the research challenges? So here is just a tiny graph of a pathfinding project, first prototype. And so what you see here is, to the right is kind of an increasing complexity, and the lower the better. So the slowdown, the lower the better. And you see actually 3 curves. The one is you have traditional RDMA-based computing, where you're actually moving data around asynchronously. And then you have 2 curves which are more or less the same, behaving more or less the same. And this is the memory performance, memory access, data access, be it within a system or using disaggregated memory beyond different systems. And this is extremely promising. This is extremely promising, and this is a very, very first step. But what could be the next step? Where are we actually heading for? Again, recap, this is our promise. We have this magic fabric doing all the tiny little combinations of the different devices. And obviously, we have more. So the composition of what we now call a computer is done by software, building the virtual machine with completely encryption, tenant-specific characteristics, etc. And ideally, that should be done on a very fine, granular basis. And this should be done not by a DBA, that should be done by the application, ideally by the software, by the data management system. So depending on the complexity of the situation, depending on the model I want to train, when a machine learning application is running on top of the database, then I obviously have to compose my system accordingly. And it's not only composition, it's kind of flexibly rearranging, reconfiguring the system. So the idea is that in the end, we have kind of a breathing system. The system is kind of fluid, and whatever we know as a computer by now is then just a sphere of control where all my data is kind of sitting where it is. I don't have to move it. I can actually mount it to my compute logic. And this kind of interplay, working with this breathing system, This is what we are actually looking at in my institute. So the question is this, well, yet another step forward, or is this really disruptive? So let's actually recap what is disruptive and what is the driver for disruption. So disruption means there is really a next step forward, and my claim is for disruption in our context, we always have two ingredients. The first one, we have to have the enabling technology, but on the other hand, we have to have the exploiting application capabilities. So asking the question, is this looking forward, this breathing, these fluid computers, is this disruptive? And my claim is, as a researcher, what we have seen so far, absolutely yes. Simply because this is finally the ultimate enabler for implementing a separation of compute and store. And that allows us that we can keep the data where it is, we keep it in the storage, we keep it in the memory, we have kind of a transparent system, and then wherever it's used, whenever it has to be used, we can actually mount our data and actually work directly on our data set. So we can actually implement elasticity, but using that virtual magic fabric, we can also implement variety. We can sprinkle in whenever we need a TPU for training a machine learning model, whenever we need GPUs or FPGAs accelerations, we just plug them in. The second key question is, does it come for free? So is it hard to exploit? And unfortunately, yes, I think so. And so this is what we are actually tackling and looking, so what does it actually take to build the next generation data management platform for those kinds of infrastructures? We are funded by the German Science Foundation, by the European Union, and obviously as a researcher we are writing papers and presenting our papers at conferences, but we are not only producing papers, we are also making our hands dirty, we are also implementing stuff. So we joined forces and we have created a European initiative on a new platform which is striving to exploit these kinds of technologies. So the project name is Daphne. So you can see there are multiple European academic institutions joining forces, working together for implementing such a new framework for traditional data management, supporting AI workloads, on the one hand, for being on the laptop, where we are able to develop your model. You start with small data sets, and then you deploy it on the HPC system. And this is all one program, this is all one platform. It's completely transparent for the user. So here in Dresden, we are responsible for, of course, hardware, software, co-design. This is our focus on the acceleration part. And what we actually have built, and this is also a bit for the techies among us, it's what we call a smart storage system. So the idea is, what are the minimal primitives? What can we actually offer from a storage perspective? What should actually be offered from a storage perspective to the higher levels of the software? This smart storage system has compression as kind of first-class citizens, is vectorizations as first-class citizens, to sprinkle in some technical buzzwords here. The core idea is you only have one code base, and you can deploy it on every piece of hardware which has kind of a processing unit. So this is part of this Daphne system. So Daphne system is using this smart storage. And on the other hand, we also plug this in and heavily invest and push for computational storage. So we ask ourselves, where can we actually place this smart storage? Where does it actually reside? And the lower, the better in our software hardware architecture stack. So in a joint effort with the IT University in Copenhagen, we have started to implement the first data management logic primitives right at the storage, right at the SSD layer, NVMe layer. We call this Delilah. as I mentioned, together with the research group from Copenhagen, we are already able to have queries, different queries, and we are able to push down certain fragments of the queries, have kind of a communication between the upper layer, the compute layer, and the lower level, the store layer, which is providing certain capabilities. And what we also can see is we are doing very, very well, not only in performance. Maybe in performance we could even do better, but that was not really the first part. The first part is we want to avoid data movement. Moving data is evil, number one. And the second one is we want to free CPU resources, then they can actually do other stuff. So I think it's kind of time to wrap up. I hope I took you a little bit to a journey of an academic, of a database person, somebody sitting on top of storage, is eager to exploit storage, is eager to push down functionality at the storage level. I hope I was able to convey you a little bit that whatever we know as a traditional computer is kind of gone. Of course, in some places that will stay. But that we are moving in the midterm to this breathing sphere of controls, what we now call the computer. That this is the driver, this is the enabler for separation of compute and store, for real separation of compute and store. I hope I was able to convey you a little bit in terms of what we are doing in Dresden, but not only in Dresden, in a larger context in a European community, devising a new platform for data-intensive applications from a laptop to HPC, from a high-level language down to the implementation and support of a plethora of different hardware devices. That's it from my side. It was my pleasure. Thank you so much.